Imagine looking up at the night sky and realizing that humanity is no longer just an observer of the cosmos. We're becoming active participants in its story. Every flicker of light, every distant star, holds the potential for discovery, and right now, there are 30 space missions unfolding that could change everything we know about our place in the universe. From planting the first footprints on Mars to launching probes that will journey beyond our solar system, these missions aren't just about exploration, they're about redefining what's possible. We're standing on the edge of a new era, one where the boundaries of science, technology, and human ambition are being pushed further than ever before. And today, we're diving deep into the most groundbreaking projects that could shape the future of space travel and our species. Think about this for a moment. Less than a century ago, the idea of humans leaving Earth's atmosphere was science fiction. Now we're planning permanent settlements on other worlds, sending robots to drill into icy moons in search of life, and designing spacecraft that could reach the nearest stars within a human lifetime. These missions aren't just about answering age-old questions, they're about survival, curiosity, and the relentless drive to explore. What if we found evidence of microbial life on Europa? What if we cracked the code for sustainable living on Mars? The implications would ripple across generations, reshaping not just science but philosophy, culture, and our very identity as a spacefaring civilization. This isn't just a list, it's a roadmap to the future. Each of these 30 missions carries the weight of human ingenuity, from daring robotic explorers venturing into the unknown to colossal telescopes that will peer deeper into the universe than ever before. Some will fail, some will revolutionize our understanding, but every single one has the potential to alter the course of history. So strap in, because we're about to embark on a journey through the most ambitious, audacious, and awe-inspiring space missions that could change everything. And by the end, you might just see the night sky a little differently. For the first time in more than 50 years, humans are preparing to walk on the lunar surface, but this time we're not just leaving footprints. NASA's Artemis program is far more than a repeat of the Apollo era. By 2025, astronauts will return to the moon with an entirely new mission, to build a sustainable presence that could serve as a stepping stone to Mars. This isn't about planting flags, it's about laying foundations. Artemis aims to establish a long-term lunar base near the moon's south pole, where shadowed craters may hold vast deposits of water ice. If accessible, that ice could be transformed into drinking water, breathable oxygen, or even rocket fuel, turning the moon into a cosmic gas station for deeper space exploration. At the heart of this ambitious plan is the Lunar Gateway, a small space station that will orbit the moon like a celestial waypoint. Unlike the International Space Station, the Gateway isn't designed for permanent crewed operations. It's a hub for science, technology testing, and staging missions to the lunar surface. Think of it as a high-tech pit stop where astronauts can prepare before descending to the moon or refuel before venturing further into the solar system. What makes this even more groundbreaking is the international collaboration behind it. Space agencies from Europe, Japan, Canada, and others are contributing key components, proving that humanity's next giant leap won't be taken by one nation alone. But the real test lies in the unproven technologies Artemis will pioneer. From next-generation spacesuits that protect astronauts from the moon's razor-sharp dust to advanced life support systems that recycle resources with near-perfect efficiency, every innovation is a dress rehearsal for Mars. The moon's lower gravity and proximity to Earth make it the perfect proving ground. If we can't sustain a lunar outpost, how could we ever hope to survive the 18-month journey to the Red Planet? Success here doesn't just mean unlocking the moon's secrets, it means rewriting the playbook for human deep space exploration. And with the first crewed Artemis landing just around the corner, the countdown to a new chapter in history has already begun. The true genius of Artemis lies not just in returning to the moon, but in transforming it into a springboard for humanity's interplanetary future. Picture a lunar outpost where astronauts don't just conduct experiments, but extract resources that could power civilization for centuries. That's the potential of helium-3, a rare isotope trapped in the moon's dusty regolith. Here on Earth, helium-3 is vanishingly scarce, but on the moon, scientists estimate there could be over 1 million metric tons embedded in the soil. Why does this matter? Because helium-3 is the holy grail of fusion energy, a clean, nearly limitless power source that could replace fossil fuels without radioactive waste. While fusion reactors are still in development, the moon could one day become the OPEC of the space age, with lunar mining operations fueling Earth's energy grid and powering colonies across the solar system. But before we reach that future, Artemis must solve the puzzle of living off the land. Unlike Apollo's brief visits, sustained lunar habitation demands radical self-sufficiency. Imagine greenhouses growing food under artificial sunlight, 3D printed shelters built from compressed moon dust, and rovers that harvest water ice to split into hydrogen and oxygen. Every drop of water, every breath of air would need to be recycled with near-perfect efficiency, a technology that's equally vital for Mars missions. The moon's low gravity also offers a unique testbed for manufacturing in space. Think about it, constructing massive telescopes or spacecraft in lunar orbit would be far easier than launching them from Earth's deep gravity well. The same principles could eventually allow us to build interstellar arcs right here in our celestial backyard. Perhaps most thrilling is how Artemis reshapes the economics of spaceflight. The moon could become the ultimate launch pad, its weak gravity requiring far less fuel to send missions toward Mars or the asteroid belt. Picture lunar spaceports stocked with fuel derived from water ice, servicing spacecraft too large to launch from Earth. This isn't science fiction. NASA are already planning depots where Mars-bound crews could dock and resupply before their 18-month journey. And with private companies racing to develop lunar landers and habitats, we're witnessing the birth of a true space economy, one where the moon isn't just a destination, but the first link in a chain stretching across the solar system. Artemis is more than a mission. It's the blueprint for how humanity becomes multiplanetary. Every solar panel deployed, every seed sprouted in lunar soil, every ounce of helium-3 extracted brings that future closer. The moon is our proving ground, our resource depot, and ultimately our gateway to the stars. SpaceX's Starship isn't just another rocket. It's a revolution wrapped in stainless steel, designed to carry humanity beyond Earth in ways we've only dreamed of. Picture a spacecraft towering nearly 400 feet tall, capable of lifting over 100 people or 100 metric tons of cargo into orbit. And here's the kicker, it's fully reusable. Unlike traditional rockets that burn up or crash after a single use, Starship is built to land, refuel, and fly again, dramatically slashing the cost of space travel. Imagine a future where hopping to Mars costs no more than a luxury car, opening the cosmos not just to governments and billionaires, but to everyday explorers. That's the disruptive power of Starship's design, turning science fiction into a business plan. Elon Musk's vision for Starship goes far beyond transportation. It's about building a second home for humanity. The ultimate goal, a self-sustaining city on Mars, a bustling colony where thousands, then millions, could live, work, and thrive. But getting there requires more than just a ride. Starship is engineered as a cosmic workhorse, equipped to haul the infrastructure needed to survive the red planet's harsh environment. Solar arrays, hydroponic farms, even 3D printers to construct habitats from Martian soil. Musk envisions fleets of starships launching in synchronized waves during Mars's closest approach to Earth every 2 years, creating a steady migration pipeline. It's an audacious timeline, aiming for the first uncrewed test landing as early as 2029. but the sheer scale of ambition forces us to rethink what's possible. What makes Starship truly groundbreaking isn't just its size or reusability, but its potential to democratize space. Traditional missions are meticulously planned, taxpayer-funded, and risk-averse. Starship flips that model, embracing rapid prototyping and accepting failure as part of progress. SpaceX's test, fly, explode, iterate approach has already shattered aerospace norms, proving that innovation thrives when you're willing to push boundaries. Each fiery test, whether a high-altitude belly flop or a controlled landing, teaches engineers more than a decade of simulations. And with plans to refuel starships in orbit using depot ships, the spacecraft could become the interplanetary equivalent of a cargo freighter, shuttling between Earth, the Moon, and Mars with routine efficiency. Yet the biggest challenge isn't engineering its biology. Surviving Mars demands solutions for radiation exposure, muscle atrophy, and the psychological toll of isolation. Starship's design hints at solutions: shielded crew quarters, artificial gravity through rotation, and even onboard greenhouses to supplement food supplies. But the real test will come when the first pioneers step onto Martian soil, tasked with turning a dead world into a home. Musk's timeline may be optimistic, but the ripple effects are undeniable. Every innovation spawned by Starship, from methane-fueled Raptor engines to orbital refueling, pushes the entire industry forward. Whether or not Mars becomes a reality within our lifetimes, Starship is already changing the game, proving that the next giant leap doesn't have to wait for governments to lead the way. This isn't just about rockets, it's about rewriting humanity's future in the cosmos. With each successful test, each iteration, Starship brings us closer to a day when Mars isn't a distant dream but a destination. And that changes everything. At the core of Starship's game-changing potential are its Raptor engines, a technological marvel that defies conventional rocketry. Unlike traditional engines that burn kerosene, Raptors use methane, a fuel choice that seems counterintuitive until you consider the bigger picture. Methane packs less punch than hydrogen, but offers a sweet spot between performance and practicality. It's easier to store, less prone to causing engine corrosion, and most crucially, can be synthesized on Mars using the planet's abundant carbon dioxide and water ice. Imagine a future where starships land on the red planet, refuel using locally harvested resources, and blast back to Earth without waiting for a tanker from home. That's the kind of self-sufficiency that makes interplanetary living more than just a pipe dream. But raw power isn't the only breakthrough. Raptor engines are also fully reusable, designed to endure dozens of flights with minimal refurbishment. Compare that to the disposable rockets of today, where millions of dollars literally go up in smoke with every launch. SpaceX's iterative testing, famously punctuated by fiery explosions, has refined Raptors to a point where they can throttle with precision, enabling the spacecraft's daring belly flop maneuver during descent. This isn't just engineering bravado, it's a fundamental shift in how we approach spaceflight, treating rockets more like airplanes than one-time fireworks. The real magic, though, happens in orbit. Starship's architecture relies on a concept called in-space refueling, where tanker versions of the spacecraft dock with crewed or cargo starships to top up their fuel reserves. Picture this: a Starship launches from Earth with just enough propellant to reach orbit, where it rendezvouses with a waiting tanker. That tanker, having flown up earlier with a full load of methane and oxygen, transfers its fuel like a cosmic gas station. Suddenly, the main Starship has enough fuel to reach Mars without the need for a gargantuan, impractical rocket. This choreography could cut the cost of interplanetary missions by a factor of 10, turning Mars into a viable destination rather than a budgetary fantasy. And that's where the economics get revolutionary. Traditional spaceflight operates like a luxury yacht, expensive, exclusive, and painstakingly handcrafted. Starship flips the model, aiming for the efficiency of a commercial airliner. SpaceX estimates that once operational, a single Starship launch could cost as little as $2 million, cheaper than some private jet flights. That's not just a leap, it's a quantum drop in pricing, opening the door for universities, startups, and even individuals to book a ride to orbit. Suddenly, lunar hotels, asteroid mining, and Martian research bases transition from sci-fi tropes to legitimate business proposals. What often gets overlooked in flashy tech discussions is the human element. Starship's spacious interior, modeled to hold up to 100 passengers, isn't just about brute capacity. It's designed for livability, with communal areas, large windows for morale-boosting views, and even potential for artificial gravity through slow rotation during long transits. These aren't the claustrophobic capsules of early spaceflight. They're prototypes of interstellar arcs built with the psychology of pioneers in mind. The implications ripple far beyond Mars. Affordable, high-capacity launches could flood orbit with next-gen telescopes, unlocking secrets of dark matter. They could enable kilometer-scale space solar power stations, beaming clean energy back to Earth, or even serve as lifeboats for asteroid deflection missions, leveraging Starship's payload capacity to haul planetary defense systems into position. This isn't just a new rocket, it's a key that unlocks every dream we've ever had about becoming a spacefaring civilization. Yet for all its promise, Starship's greatest legacy may be cultural. By demystifying space travel, it shifts humanity's mindset from if to when. Kids today aren't just dreaming of being astronauts, they're planning what to pack for Mars. Scientists debate not whether we'll find life elsewhere, but how soon we can go look. That psychological shift, more than any engine or fuel depot, is what makes Starship a hinge point in history. The future isn't waiting, it's fueling up on the launch pad. While Mars and the Moon dominate headlines, some of the most profound discoveries in our solar system may be waiting 500 million miles away, hidden beneath the icy crusts of Jupiter's mysterious moons. The European Space Agency's JUICE mission, short for Jupiter Icy Moons Explorer, is on a quest to uncover secrets that could rewrite our understanding of life's potential beyond Earth. Slated to arrive in 2031 after an 8-year journey, this ambitious spacecraft carries a suite of instruments so advanced they're essentially a cosmic detective kit designed to probe the hidden oceans of Ganymede, Callisto, and Europa. These aren't just frozen wastelands, they're dynamic worlds with subsurface seas that may hold more liquid water than all of Earth's oceans combined. What makes JUICE so revolutionary is its precision targeting. Unlike previous flybys that offered fleeting glimpses, this mission will spend years meticulously studying Ganymede, the solar system's largest moon, and the only one with its own magnetic field. Imagine an icy sphere so vast it dwarfs Mercury, with a hidden ocean that could stretch 60 miles deep beneath its crust. JUICE radar will penetrate that ice, mapping subsurface structures in unprecedented detail, while its laser altimeter measures minute changes in surface elevation, clues to the ocean's currents below. Even Ganymede's thin oxygen atmosphere will be scrutinized for organic molecules, potential fingerprints of chemical processes that could support life. But the real showstopper might be Europa, a moon with plumes of water vapor erupting from cracks in its gleaming ice shell. JUICE won't orbit Europa, that honor goes to NASA's upcoming Europa Clipper, but its high-resolution cameras and spectral analyzers will capture critical data during close flybys. The goal, to identify compounds like salts and complex organics on the surface that could hint at hydrothermal activity in the ocean below. Scientists speculate that Europa's seafloor might host vents similar to Earth's deep-sea hydrothermal systems, hotspots teeming with extremophile life forms. If JUICE detects the right chemistry, it could bolster the case for sending a future lander to drill through the ice. Callisto, often overshadowed by its more glamorous siblings, offers a different kind of prize. Its ancient cratered surface is a frozen archive of the solar system's violent past, while its subsurface ocean, though less studied, could be remarkably stable. JUICE will map Callisto's gravitational anomalies to pinpoint where liquid might lurk, providing clues about how such oceans form and persist over billions of years. The Moon's relatively low radiation levels also make it a prime candidate for future human outposts, a cosmic way station for missions deeper into the Jovian system. Powering this scientific arsenal requires ingenious engineering. At Jupiter's distance, sunlight is 25 times weaker than on Earth, so JUICE relies on solar panels the size of tennis courts, the largest ever flown on an interplanetary mission. Its instruments must operate in brutal radiation belts that could fry conventional electronics, shielded by special coatings and redundant systems. Even communication is a feat. Signals take nearly an hour to travel back to Earth, forcing the spacecraft to make autonomous decisions during critical observations. The implications of JUICE findings could ripple far beyond planetary science. Confirming habitable conditions on these moons would challenge our definitions of where life can thrive, turning gas giant systems into new frontiers for astrobiology. And if the mission detects even indirect signs of biological activity, like skewed ratios of certain isotopes or unexpected chemical gradients, it would ignite a firestorm of follow-up missions. We might be standing at the threshold of answering one of humanity's oldest questions. Are we alone in the universe? JUICE represents more than technological prowess. It's a testament to patience and long-term thinking. Conceived in the 2000s, launched in 2023, and delivering results in the 2030s, this mission spans generations. But when that first data packet arrives, revealing the secrets of alien oceans that have existed since the dawn of the solar system, the wait will feel like a blink in cosmic time. Imagine a world where rain falls not in droplets of water, but in liquid methane, where rivers carve valleys through icy dunes, and the atmosphere is so thick you could strap on wings and fly. This isn't a scene from a distant exoplanet. It's Saturn's largest moon, Titan, and NASA's Dragonfly mission is about to turn it into the ultimate extraterrestrial exploration playground. Slated to launch in 2027, this nuclear-powered drone isn't just another rover. It's a revolutionary flying machine designed to hop across Titan's alien landscape, sampling its organic-rich soil and studying conditions that might mirror Earth before life began. Titan has long fascinated scientists as a time capsule of primordial chemistry. Its thick nitrogen atmosphere, laced with methane and complex hydrocarbons, resembles what Earth's might have been billions of years ago, but frozen in time. What makes Dragonfly extraordinary is its ability to exploit Titan's unique environment. With gravity just 1/7 of Earth's and an atmosphere 4 times denser, flying is far more efficient than driving. Picture a drone the size of a compact car, powered by a radioisotope thermoelectric generator, essentially a nuclear battery, soaring between sites dozens of miles apart, each chosen for its potential to unlock secrets about how life's building blocks form. The science targets are staggering. Dragonfly will touch down near Titan's equatorial dunes, where Cassini's earlier observations detected vast fields of organic sand. These grains aren't silica like Earth's deserts. They're likely made of frozen hydrocarbons like benzene, sculpted into eerie shapes by methane winds. The drone's drill will collect samples, analyzing them with an onboard mass spectrometer to identify amino acids, nucleotides, and other molecules critical for life. But the real jackpot lies in Titan's methane lakes. At the moon's poles, liquid methane and ethane form vast seas, complete with waves and shorelines. Dragonfly won't land on these lakes, but it will study regions where wet and dry chemistry mix, simulating the primordial soups that may have sparked life on Earth. Powering this mission so far from the Sun demands innovation. solar panels are useless in Titan's dim, hazy skies, so Dragonfly relies on plutonium-238, which decays to produce heat converted into electricity. This same technology powered Mars' Curiosity rover, but Dragonfly pushes it further. Its rotors must operate in -290 degrees Fahrenheit, where materials become brittle and electronics sluggish. Yet these challenges pale next to the payoff. If Titan's chemistry shows signs of progressing toward life, even if life itself isn't present, it would suggest that the universe is teeming with environments where biology could emerge. Beyond astrobiology, Titan's methane cycle offers a mirror to Earth's water cycle, but with a twist. Here, methane evaporates from lakes, forms clouds, and rains back down, creating weather patterns we can study as alien analogues to our own. Dragonfly's meteorological sensors will track these processes in real time, offering insights into climate dynamics that could reshape planetary science. And let's not forget the engineering spectacle watching a nuclear-powered drone navigate an alien sky, sending back images of hydrocarbon rivers and organic dunes, will captivate imaginations worldwide. Dragonfly isn't just visiting Titan, it's opening a window into a parallel evolutionary path, one where the ingredients for life mix under a cold orange haze. Whether it finds probiotic chemistry or just more questions, this mission will redefine our understanding of life's cosmic potential. And by the time Dragonfly's rotors fall silent, we may finally grasp how rare or how common worlds like ours truly are. China's Tianwen-3 mission represents more than just another rover on Mars. It's the opening move in a high-stakes race to unlock the red planet's deepest secrets. While NASA and the European Space Agency collaborate on their own sample return effort, China is charging ahead with an ambitious solo plan to land, collect, and rocket Martian soil back to Earth by 2030. If successful, this would mark humanity's first ever round-trip ticket to Mars, delivering pristine samples that could reveal whether the planet ever harbored life. But what makes Tianwen-3 stand out isn't just the destination. It's the breakneck engineering feats required to pull off a mission even NASA considers one of the hardest in planetary science. The mission builds on China's rapid advancements in deep space exploration. Remember Tianwen-1, the 2021 mission that placed both an orbiter and the Zhurong rover on Mars in a single launch. Tianwen-3 takes that expertise to the next level with a two-part architecture. First, a lander will touch down near Utopia Planitia, a vast basin where Zhurong previously spotted possible evidence of ancient water. Unlike NASA Perseverance rover, which caches samples for later pickup, China's lander will drill directly into Martian soil, packaging core samples into sealed containers within hours of arrival. Speed is critical. Mars's dust storms and radiation can degrade organic molecules, so the sooner samples are secured, the better their scientific value. But here's where the real magic happens. A second spacecraft, launched separately, will rendezvous with the samples in Martian orbit, a first-of-its-kind docking maneuver beyond Earth. This orbiter carries a return capsule equipped with a heat shield tough enough to survive the fiery plunge through Earth's atmosphere. The precision required is staggering. Imagine coordinating two spacecraft across hundreds of millions of miles with signal delays of up to 20 minutes to successfully transfer a coffee can-sized container of Martian dirt. Fail any step and the prize could be lost forever in space or burned to ashes on re-entry. Scientifically, the payoff could reshape our understanding of Mars's potential for life. Utopia Planitia's terrain holds layers of sediment deposited billions of years ago when water likely flowed across the surface. By analyzing isotopes, mineral patterns, and even trapped gas bubbles in these samples, researchers could piece together the planet's climatic history. Was Mars once warm and wet long enough for life to emerge? Even more tantalizing, if Tianwen-3 detects complex organic molecules or mineral signatures associated with microbial activity, it would bolster the case for sending humans to search for fossilized evidence firsthand. Politically, the mission signals China's rise as a space superpower. A successful return would place them in an elite club of nations capable of interplanetary round trips, leapfrogging traditional rivals. But the mission also raises questions about planetary protection, how to ensure Martian material doesn't contaminate Earth's biosphere. China has disclosed few details about its sample handling protocols, leaving international scientists cautiously optimistic but keen for transparency. One thing's certain, whichever nation unlocks Mars's secrets first will write the next chapter in humanity's cosmic story. And with Tianwen-3's timeline aggressive yet achievable, that chapter might begin sooner than anyone expected. Picture holding a spacecraft in the palm of your hand, a tiny silicon chip no larger than a postage stamp, yet capable of journeying to another star. That's the radical vision behind Breakthrough Starshot, an initiative that sounds more like science fiction than actual science. The plan, to launch a fleet of nanocraft, each weighing just grams, toward Alpha Centauri, our nearest stellar neighbor, and propel them to 20% the speed of light using nothing but the power of focused lasers. At that velocity, these microprobes could reach the Alpha Centauri system in just 20 years, snapping the first ever close-up images of an exoplanet as they whiz by. It's an idea so bold it redefines the boundaries of interstellar travel, turning what was once a multi-generational pipe dream into a project with a conceivable timeline. The engineering behind this feat is as breathtaking as the mission itself. Each nanocraft or starship would carry cameras, sensors, and a tiny light sail, an ultra-thin reflective sheet designed to catch the push of photons from a massive ground-based laser array. Imagine a 100-gigawatt laser beam, 10 million times more powerful than a standard household laser pointer, firing into space and striking sails the size of a picnic blanket. The force isn't much about the weight of a snowflake, but in the frictionless vacuum of space, that gentle nudge accelerates the nanocraft to mind-bending speeds. Within minutes, they'd be traveling faster than any human-made object in history, covering the distance to the moon in under 10 seconds. But the challenges are as immense as the ambition. Keeping a laser beam perfectly focused over millions of miles is like threading a needle from across a football field while both the needle and the thread are moving. Even the tiniest deviation could send the nanocraft spinning off course, lost forever in the void. Then there's the issue of interstellar dust particles no larger than a grain of sand could vaporize a probe on impact at such velocities. Engineers propose embedding tiny deflectors or designing self-healing materials, but these solutions remain untested. And perhaps most daunting of all, how to transmit data back to Earth across 4.3 light-years. The plan: equip each nanocraft with a miniature laser transmitter, no brighter than a candle flame, and rely on Earth's most sensitive telescopes to detect its faint signal. The scientific payoff could reshape our understanding of the cosmos. Alpha Centauri's planets, particularly Proxima Centauri b, orbit in the habitable zone where liquid water might exist. Starshot's flyby images could reveal surface features, oceans, continents, even signs of vegetation or artificial structures. For context, consider how Hubble's blurry glimpses of Pluto were replaced by New Horizons' stunning high-res portraits. Starshot aims to do the same for worlds light-years away. Even a single pixelated image of an exoplanet's surface would dwarf every discovery made by telescopes to date. Critics argue the project leans too heavily on technologies that don't yet exist, from lightweight power sources to laser arrays spanning kilometers. Yet proponents counter that every component, optical lasers, miniaturized electronics, light sails, is already in early development. The real hurdle isn't physics, it's scaling these technologies to Starshot's extraordinary requirements. And with backers like Yuri Milner and Stephen Hawking's legacy fueling the effort, the project has both the funding and the vision to push boundaries. Breakthrough Starshot isn't just about reaching the stars, It's about proving that humanity can think beyond rockets and chemical propulsion. If successful, it could pave the way for larger probes or even crewed missions using the same laser highway. The nanocraft themselves might be fleeting, their flybys lasting mere hours, but the data they beam home could echo through centuries. In a universe where distances seem designed to humble us, Starshot dares to ask, what if the stars aren't as far away as they appear? Beneath Europa's cracked, icy surface lies an ocean so vast it could drown all of Earth's continents twice over. And NASA Europa Clipper is humanity's best shot at uncovering its secrets. Unlike any mission before it, this spacecraft won't just fly past Jupiter's enigmatic moon. It'll conduct nearly 50 close passes, skimming as low as 16 miles above the surface to map every fracture, plume, and hidden pocket of liquid water. Armed with a suite of 9 cutting-edge instruments, Clipper isn't hunting for aliens outright. It's assembling the clues to answer a far bigger question. Could this frozen world, bathed in Jupiter's relentless radiation, actually harbor the ingredients for life? The key lies in Europa's chaotic terrain. From orbit, the moon looks like a shattered marble, its surface crisscrossed with reddish-brown scars and towering ice ridges. These features hint at a subsurface ocean in constant motion, flexed by Jupiter's gravitational tug. Clipper's ice-penetrating radar, Reason, will peer through miles of ice to gauge the ocean's depth and salinity, while its thermal imager will scan for hotspots where liquid might erupt through geysers. But the real game-changer is the surface dust analyzer, which will catch microscopic particles ejected from these plumes. A cosmic taste test that could reveal organic molecules or even fragments of microbial life lifted from the depths. What makes Europa so tantalizing isn't just the presence of water, but its chemistry. Earth's hydrothermal vents thrive with life in utter darkness, fueled by chemical reactions between seawater and hot rock. Europa's seafloor, heated by the same gravitational kneading that cracks its surface, might host similar ecosystems. Clipper's ultraviolet spectrograph will hunt for sulfur and carbon compounds in the plume's telltale signs of seafloor activity. Even more compelling, the spacecraft's magnetometer will measure the ocean's conductivity. Saltier water conducts electricity better, and if the readings match Earth's oceans, it would suggest Europa's waters have been leaching minerals from rock for eons, creating a primordial soup ripe for life's spark. Yet the mission's brilliance lies in its restraint. Clipper won't land or drill through the ice, that's for a future mission. Instead, it's playing the ultimate detective, gathering enough evidence to justify the next daring leap, a robotic submersible. Every plume sample analyzed, every thermal anomaly mapped, brings us closer to confirming whether Europa's ocean is merely fascinating or truly habitable. And with a launch window opening as early as 2024, we might have answers before this decade's end. One thing's certain, if Clipper finds even a whiff of the right chemistry, Europa will rocket to the top of humanity's exploration agenda, forever changing how we see our place in the cosmos. India's Gaganyaan mission isn't just about launching astronauts, it's a statement. A declaration that the world's most populous democracy is ready to carve its name among the stars. By 2025, if all goes according to plan, 3 Indian astronauts could be circling Earth in a fully indigenous spacecraft propelled by rockets built on homegrown technology. This would place India in an elite club alongside the United States, Russia, and China as the only nations to have independently sent humans to space. But Gaganyaaan's significance runs deeper than national pride. It's a catalyst, igniting India's aerospace industry, inspiring a generation of engineers, and proving that space exploration isn't just for superpowers with decades of experience. The mission's architecture showcases India's knack for cost-effective innovation. Unlike NASA Orion or Russia's Soyuz, Gaganyaaan's crew module is compact, designed to carry 3 astronauts for up to a week in low Earth orbit. The launch vehicle, a modified version of India's proven J-SLV Mark III rocket, affectionately nicknamed Bahubali after a mythological strongman. But what's truly remarkable is the price tag. At an estimated $1.5 billion, the entire program costs less than a single Falcon Heavy launch. This frugality stems from India's ability to repurpose existing technology, like adapting the capsule's design from its uncrewed lunar and Martian probes. Yet human spaceflight introduces challenges beyond engineering. Astronaut training, life support systems, and emergency escape mechanisms all had to be developed from scratch. India turned to Russia for initial cosmonaut training, but the Vikram Sarabhai Space Center has since built its own facilities, including a centrifugal simulator to acclimate crews to intense G-forces during re-entry. The spacecraft itself incorporates redundant safety systems, from parachute backups to a crew escape module that can jettison the capsule mid-launch if disaster strikes. These aren't just technical hurdles, they're cultural milestones, transforming India from a nation known for satellite launches to one capable of keeping humans alive in the void. Beyond symbolism, Gaganyaan lays groundwork for India's cosmic ambitions. A successful mission would pave the way for an indigenous space station by 2035, positioning India as a key player in the new space economy. Already, private Indian startups are emerging to supply components, creating an ecosystem that could rival SpaceX or Blue Origin in the coming decades. And let's not forget the international ripple effects. Countries across Asia and Africa now see India as proof that space isn't an exclusive club, but a frontier open to all who dare reach for it. The real magic, though, lies in Gaganyaaan's ability to inspire. When those astronauts lift off from Sriharikota, millions of Indian children will watch, dreaming of their own journeys to the stars. That's the untold power of human spaceflight, not just the science or the politics, but the spark it ignites in the next generation. And with India's methodical, budget-conscious approach, this mission may well redefine how humanity thinks about reaching orbit, proving that sometimes the boldest leaps come from the most unexpected places. Since landing in Jezero crater in 2021, NASA Perseverance rover has been rewriting the textbook on Mars, uncovering clues that suggest this barren world was once a thriving aquatic paradise. Its most jaw-dropping find, layers of sedimentary rock along the crater's ancient river delta, concrete evidence that water once flowed here for tens of millions of years, long enough for life to have taken hold. But Perseverance isn't just collecting data, it's packing souvenirs. Using a drill more sophisticated than a dentist's tool, the rover has been sealing pristine samples of Martian rock and soil into titanium tubes, each no larger than a marker pen. These aren't just geological curiosities, they're time capsules from an era when Mars may have resembled early Earth, and soon they could be hurtling toward our planet in one of the most ambitious space missions ever attempted. Enter the Mars Sample Return Campaign, a transatlantic handshake between NASA and the European Space Agency to bring these cosmic treasures home by 2033. The logistics read like a sci-fi heist. First, a rocket-powered fetch rover will land near Perseverance, load the cached tubes into a protective capsule, then blast them back into Martian orbit. There, a European-built spacecraft acting as an interplanetary courier will snag the basketball-sized container mid-flight and slingshot it toward Earth. The precision required is mind-bending. Imagine catching a bullet with another bullet, except both are traveling at thousands of miles per hour, and the second bullet has to launch itself across 40 million miles of space first. Why go through all this trouble? Because labs here have tools no rover could ever carry. Electron microscopes can scan samples atom by atom, searching for fossilized microbes or organic molecules degraded by Mars's radiation. Mass spectrometers might detect isotope patterns unique to biological processes. Even the tiniest gas bubble trapped in rock could reveal what Mars's atmosphere was like billions of years ago, clues to why it went from wet and warm to dry and frigid. These samples could settle the debate over whether life ever existed beyond Earth, and by extension, whether it's lurking elsewhere in our solar system. Yet the mission's real genius lies in its contingency plans. Perseverance isn't just stashing samples, it's creating backups. If the Fetch rover fails, 2 helicopters based on Ingenuity's design stand ready to retrieve tubes left as trail markers. The orbiter can loiter for years if needed, waiting for another shot. Every redundancy speaks to the value of these Martian fragments. They're not just rocks, but potential Rosetta Stones for decoding the origins of life itself. The stakes couldn't be higher. Success would mark humanity's first round trip to another planet, proving we can retrieve objects from worlds beyond our moon. But more than that, it would set the stage for future missions to Europa's ice or Titan's dunes, places where sample return might be our best shot at finding extraterrestrial life. Perseverance's tubes may hold the answer to whether life is a cosmic fluke or a universal inevitability. And if all goes to plan, we won't have to wait generations to find out. While NASA Artemis Program grabs headlines for putting boots back on the moon, there's another player quietly reshaping lunar exploration: Blue Origin's Blue Moon lander. Jeff Bezos's aerospace venture isn't just building a spacecraft, it's engineering the cornerstone of a lunar economy designed to ferry cargo, equipment, and eventually cruise to the moon's surface with the precision of an Amazon delivery truck. What sets Blue Moon apart isn't its size, though its payload capacity rivals a small school bus, but its vision. This isn't a one-off mission. It's the first step toward a future where the moon isn't just explored, but industrialized, with Blue Origin positioning itself as the freight hauler of choice for scientists and entrepreneurs alike. Blue Moon's design reads like a wish list for sustainable lunar operations. Its hydrogen-fueled engines, while complex, offer a game-changing advantage: the ability to refuel using water ice mined from the moon's poles. Imagine a lander that doesn't just touch down and depart, but stays on the surface as a permanent depot, its tanks refilled by rovers harvesting frozen water from shadowed craters. That's the kind of closed-loop system that could turn the moon from a destination into a hub, and Blue Origin is betting big on the infrastructure to make it happen. The lander's modular architecture allows for everything from science payloads to crewed cabins, adapting to missions as diverse as deploying telescopes or assembling solar farms. But Blue Moon isn't flying solo. It's a critical piece of NASA Artemis puzzle. Selected as one of the program's commercial partners, Blue Origin will deliver cargo ahead of human landings, prepositioning habitats and rovers so astronauts arrive to a ready-made workspace. The collaboration is a masterclass in public-private synergy. NASA provides funding and lunar expertise, while Blue Origin brings Silicon Valley's rapid iteration ethos. Early mock-ups already showcase innovations like a crane arm capable of unloading multi-ton payloads autonomously, a necessity for operations in the moon's harsh, low-gravity environment. The long-term play, though, is even bolder. Blue Origin's concept art reveals sprawling lunar bases powered by nuclear reactors, with Blue Moon landers shuttling between Earth and Moon weekly. Bezos envisions a future where heavy industry, think semiconductor manufacturing or solar panel production, moves off-world, leveraging the moon's low gravity and abundant raw materials. It's a vision that skirts sci-fi, but consider this: Blue Moon's early contracts already include partnerships with universities and startups eager to experiment in partial gravity, from 3D printing regolith bricks to testing hydroponic crops under lunar radiation. Critics argue the timeline is optimistic, given Blue Origin's slower pace compared to SpaceX. Yet the company's methodical approach has merits. Every component, from the lander's AI navigation system to its patented daisy chain solar arrays, undergoes exhaustive testing. The stakes are too high for shortcuts. A single failed landing could crater confidence in commercial lunar logistics. But if Blue Moon sticks its first touchdown, it could trigger a gold rush, proving that the moon isn't just a government playground, but the next frontier for commerce. What makes this mission extraordinary isn't the technology alone, it's the shift in mindset. Blue Moon embodies the idea that space isn't just about discovery, but about permanence. Every payload delivered, every ounce of fuel mined locally, inches us closer to a reality where moon dust on boots isn't historic, it's routine. And in that quiet revolution, Blue Origin might just become the shipping magnate of the solar system. While Mars itself has been the focus of countless missions, its two tiny moons, Phobos and Deimos, have lingered in the shadows, their origins shrouded in mystery. Japan's MMX mission, short for Martian Moons Exploration, is about to change that. Slated for launch in 2026, this audacious spacecraft will be the first to land on Phobos, scoop up samples from its surface, and potentially settle one of the biggest debates in planetary science. Are these moons captured asteroids, or did they form from debris blasted off Mars during a cataclysmic impact? The answer could rewrite our understanding of how planetary systems evolve, and MMX is packing a suite of instruments designed to crack the case. What makes Phobos and Deimos so puzzling isn't just their size. Phobos is barely 17 miles across, but their contradictory traits. Their irregular shapes and dark surfaces scream captured asteroids, yet their nearly circular orbits around Mars suggest they formed closer to home. MMX plans to resolve this by mapping both moons in unprecedented detail, using cameras and spectrometers to compare their composition to known asteroid types. But the real smoking gun could come from the mission's crown jewel, a sampler arm that will collect at least 10 grams of Phobos' regolith, sealing it in a capsule for return to Earth by 2031. Even a teaspoon of this material might hold isotopic signatures revealing whether the moons are made of Martian crust or foreign asteroid rubble. Landing on Phobos won't be easy. With gravity just 1/1000th of Earth's, even a gentle touchdown could send the spacecraft bouncing into space like a beach ball. JAXA engineers have devised a clever solution: harpoons. As MMX descends, it will fire tethered anchors to latch onto the surface, stabilizing itself long enough to drill into the loose soil. This same technology could pave the way for future missions to other low-gravity worlds, from asteroids to distant Kuiper Belt objects. Meanwhile, a German-built rover named Idefix will detach to explore nearby terrain, providing ground truth data to complement orbital observations. The mission's secondary goal is equally compelling: studying Mars's atmosphere from a front-row seat. From their unique vantage point, Phobos and Deimos pass through the red planet's tenuous outer gas layers during each orbit. MMX's plasma sensors will analyze how solar wind interacts with these gases, offering clues about how Mars lost its once thick atmosphere, and with it, the water that may have nurtured life. But the biggest payoff could be cultural. If MMX confirms Phobos is a chip off Mars's block, it would suggest giant impacts are even more common than we thought, reshaping theories about how moons form across the cosmos. Alternatively, proving these moons are captured asteroids would imply Mars's gravity net is surprisingly efficient, with implications for how planets corral wandering space rocks. Either way, the tiny samples returning to Earth might carry echoes of Mars's own history, fragments of the red planet delivered to us by its enigmatic companions. And for Japan, already a leader in asteroid sample returns, MMX cements its place as the quiet master of off-world treasure hunting. When those precious grains finally land in labs, they won't just solve a scientific debate. They'll remind us that sometimes the biggest secrets hide in the smallest places. Floating 1,000,000 miles from Earth, NASA James Webb Space Telescope isn't just rewriting the astronomy textbook, it's tearing it up and starting from scratch. Since its first images stunned the world in 2022, JWST has become the ultimate cosmic detective, peering deeper into space and further back in time than any instrument before it. But what's truly groundbreaking isn't just the telescope's ability to capture pretty pictures of nebulae, it's how it's revolutionizing our search for life beyond Earth by dissecting the atmospheres of distant exoplanets with surgical precision. Imagine a machine so sensitive it can detect the chemical fingerprint of a single molecule in the air of a world light years away. That's the power of JWST gold-plated mirrors and infrared eyes, and the discoveries are already pouring in. Take the water vapor swirling around WASP 96b, a gas giant orbiting a sun-like star 1100 light-years away. When JWST trained its spectrographs on this scorching world, it didn't just confirm the presence of H2O, it mapped the water's distribution across the planet's atmosphere in 3 dimensions, revealing how heat and wind stir the molecules into swirling patterns. That level of detail was unimaginable just 5 years ago, but the real shocker came when the telescope analyzed K2-18b, a potentially habitable super-Earth 8 times our planet's mass. Hidden in the data were tentative whispers of dimethyl sulfide, a molecule on Earth produced only by living organisms like phytoplankton. It's not proof of aliens, not yet, but it's the kind of clue that has scientists scrambling to schedule more observation time. JWST prowess extends far beyond sniffing exoplanet air. Its deep-field images have captured galaxies so ancient they shouldn't exist under current cosmological models. Mature, star-filled cities gleaming just 300 million years after the Big Bang. These cosmic toddlers, brimming with elements like oxygen and carbon far earlier than predicted, are forcing astronomers to reconsider how quickly the first stars formed and died. One leading theory suggests the early universe might have birthed monstrous, short-lived stars hundreds of times the Sun's mass, seeding the cosmos with heavy elements in a blink. Every pixel of these images holds clues to the universe's awkward adolescence, a period we're only now beginning to understand. What makes JWST uniquely terrifying for theorists is its ability to observe in infrared light, the thermal glow left over from the universe's expansion. While Hubble showed us the cosmos in visible light, JWST sees the heat signatures hidden behind cosmic dust clouds, like switching from grainy black and white film to high-definition thermal imaging. This has already upended assumptions about black hole growth rates, revealed violent stellar nurseries where planets form, and even spotted organic molecules floating in the debris around young stars. But the holy grail remains biosignatures, combinations of gases like oxygen, methane, and ozone that could indicate alien photosynthesis or microbial metabolism. The telescope's next big target, TRAPPIST-1e, an Earth-sized world orbiting snugly in its star's habitable zone, where JWST data might finally answer whether we're alone in the dark. Yet for all its power, JWST is just the beginning. Each discovery raises new questions, each answered mystery unveils 10 more. The telescope wasn't built to give us final answers, it was built to show us how much we didn't know. And as its infrared gaze keeps piercing the cosmic veil, one thing becomes clear. The universe is far stranger, far more wondrous than we ever dared imagine. 45 years and counting NASA twin Voyager probes weren't designed to last this long, and yet they continue sailing into the unknown, billions of miles beyond where any human-made object has ventured before. These interstellar pioneers, each no larger than a compact car, have redefined the boundaries of our cosmic neighborhood, proving the solar system doesn't just fade away, it ends with a bang. Voyager 1's crossing into interstellar space in 2012 was no quiet milestone. It marked the moment humanity truly stepped beyond the cradle of our sun's influence into the galactic ocean where particles from ancient supernovas dance between the stars. What makes their journey extraordinary isn't just the distance, it's the treasures they've sent back. Voyager 2's encounter with Neptune in 1989 revealed geysers erupting from Triton's icy surface, while Voyager 1 spotted volcanoes spewing sulfur on Jupiter's moon Io. But their greatest discoveries came after their planetary tours ended. As they pierced the heliosphere, the protective bubble of charged particles blown by the solar wind, their instruments recorded something startling: a turbulent, frothy boundary where the sun's influence collides with interstellar winds. Think of it as cosmic surf breaking on a celestial shore, with shockwaves rippling outward as the solar system plows through the galaxy. Even now, their faint signals whisper secrets. Voyager 1's plasma wave instrument detected the faint hum of interstellar gas, a vibration revealing the density of matter between stars. Meanwhile, Voyager 2, taking a different path out of the solar system, confirmed that the heliosphere isn't symmetrical but squashed, as if buffeted by some unseen galactic current. These findings weren't just academic, they forced us to rethink how stars shape the space around them, and how that space, in turn, affects planets like Earth. Without Voyager, we'd have no clue that our solar system's protective bubble fluctuates like a lung with the sun's 11-year cycle, potentially altering how much cosmic radiation reaches our atmosphere. Yet perhaps their most enduring legacy lies not in data but in symbolism. Each probe carries a golden record, a time capsule of Earth sounds, music, and greetings in 55 languages. Their messages in bottles hurled into the cosmic sea, likely to outlast humanity itself. Their power sources will fade by 2030, but their trajectory is set. In 40,000 years, Voyager 1 will drift within 1.6 light-years of a star in Camelopardalis, while Voyager 2 approaches Sirius in 296,000 years. They'll be silent by then, but their very presence in the void speaks to an audacious truth: that for one fleeting moment, a species on a pale blue dot reached out, touched the stars, and refused to let go. The Voyagers taught us that space isn't empty. It's alive with unseen forces shaped by stellar winds and ancient explosions. And though their instruments may soon fall silent, their journey is just beginning, a permanent testament to curiosity's boundless reach. Venus hides its secrets beneath a suffocating shroud of clouds, acidic, scorching, and so dense they crushed every lander humanity ever sent within hours. But NASA Da Vinci I+ mission isn't just another doomed visitor. It's a daredevil chemist plunging straight into the maelstrom to settle one of planetary science's hottest debates. Was this hellscape once a twin of Earth, complete with oceans and maybe even life? Slated to launch in 2029, the spacecraft will deploy a titanium-clad probe the size of a compact car, letting it free fall for 60 terrifying minutes through layers of sulfuric acid haze while sniffing for clues of a lost paradise. The stakes couldn't be higher. Recent observations of Venus's upper atmosphere detected whiffs of phosphine, a gas that on Earth is almost exclusively produced by microbes. Could it be a relic of ancient organisms that thrived before a runaway greenhouse effect boiled the oceans away, or just a fluke of exotic chemistry? Da Vinci I+'s mass spectrometer will dissect every trace of gas on its descent, hunting for isotopes and noble gases that act as cosmic fingerprints. Certain ratios of argon or neon, for example, could reveal whether Venus once had Earth-like water volumes that vanished through catastrophic evaporation. Even more tantalizing, if the probe catches phosphine deeper in the atmosphere, where temperatures and pressures mimic early Earth's shallow seas, it would ignite a firestorm of speculation about airborne life clinging on in this toxic sky. But the mission's genius lies in its dual approach. While the probe tackles atmospheric mysteries, the orbiter will map vast tessera regions, jumbled highlands that might be Venus's version of continents. Using infrared cameras to peer through the clouds, it'll search for mineral signatures like granite, which typically forms underwater on Earth. Finding it would be smoking gun evidence that Venus had not just water, but sprawling oceans that persisted for billions of years. Add in Dragonfly's ability to measure wind speeds at different altitudes, and we might finally understand how Venus's once moderate climate spiraled into a 470 degrees Celsius furnace, a cautionary tale for our own planet's future. The implications stretch far beyond one world. If Venus truly was habitable, it suggests that even planets orbiting closer to their stars might host life before succumbing to stellar warming. That expands the Goldilocks zone for exoplanet hunters, adding burned-out worlds like Venus as potential archaeological sites for extinct biology. And if by some miracle phosphine does hint at surviving microbes, it would mean life isn't just tenacious, it's everywhere, lurking in the unlikeliest corners of the cosmos. Dragonfly isn't just visiting Venus, it's investigating a crime scene, searching for clues to a planetary murder mystery billions of years in the making. And whether it finds ghosts of lost oceans or hints of stubborn life, one thing's certain, our sister planet still has stories to tell if we're brave enough to listen. SpaceX's Polaris program isn't just another billionaire space joyride. It's a high-stakes testbed for the technologies that will carry humanity to Mars and beyond. Funded by tech entrepreneur Jared Isaacman, who previously commanded the Inspiration 4 mission, this trio of crewed flights aims to push the boundaries of commercial spaceflight like never before. The first mission, Polaris Dawn, is set to rewrite the rulebook with the first ever commercial spacewalk, conducted outside a Dragon capsule in the vacuum of low Earth orbit. But the real game-changer lies in the fine print. These missions will rigorously test technologies critical for Starship's success, from in-space refueling protocols to next-gen spacesuit designs, bridging the gap between theoretical concepts and real-world readiness. Picture an astronaut floating outside Dragon, not in NASA iconic white suits, but in a sleek, SpaceX-designed extravehicular activity suit optimized for mobility. This isn't just a fashion statement, it's a prototype for the gear future Mars colonists might wear, built to handle everything from microgravity repairs to surface operations on the Red Planet. Polaris Dawn's spacewalk will put the suit through its paces, testing its ability to protect against radiation, regulate temperature, and maintain flexibility during complex tasks. The stakes, a single flaw could mean mission failure, but success could revolutionize how we approach human-robot collaboration in deep space. Beyond the spectacle, Polaris is tackling problems traditional agencies avoid. One experiment will intentionally induce decompression sickness, the dreaded BENS, to study how gas bubbles form in zero gravity, data crucial for designing emergency protocols on long-duration missions. Another will practice using Starlink satellites for deep space communication, a vital backup for astronauts venturing beyond the moon. But the most audacious goal might be testing orbital refueling techniques, quietly laying groundwork for Starship's propellant depots. Imagine Dragon rendezvousing with a dummy tanker, rehearsing the delicate dance of transferring fuel in microgravity, a skill that could one day keep starships topped up between Earth and Mars. What makes Polaris unique is its hybrid nature, straddling the line between private enterprise and NASA, a methodical approach. Isaacman's team includes both SpaceX engineers and veteran astronauts, blending Silicon Valley's move-fast ethos with hard-won operational wisdom. The program's later missions plan to push further, potentially shattering the 50-year-old record for highest Earth orbit ever reached by a crewed vehicle, a symbolic middle ground between the International Space Station and lunar space. Critics dismiss Polaris as a vanity project, but its ripple effects are undeniable. Every technology proven here, from radiation shielding to emergency medicine, shortens the learning curve for Mars. And by demonstrating that private crews can safely conduct complex operations beyond tourism, the program could open the floodgates for commercial deep space ventures. Polaris isn't just a mission, it's the missing link between orbital joyrides and interplanetary civilization, proving that the next giant leaps won't always come from governments. Sometimes they'll launch from a billionaire's vision and a generation's hunger to push further. While most telescopes focus on finding new exoplanets, ESA's Ariel mission is flipping the script. Instead of hunting for new worlds, it's diving deep into the chemistry of 1,000 already discovered planets to answer one burning question: what exactly are their atmospheres made of? Set to launch in 2029, this cosmic detective will spend 4 years scrutinizing the air around planets ranging from scorching gas giants to temperate super-Earths, searching for the molecular fingerprints that could reveal everything from weather patterns to potential signs of life. What makes Ariel revolutionary isn't just its targets, it's the sheer scale of its ambition, creating the first ever large-scale catalog of exoplanet atmospheres that will serve as a Rosetta Stone for decoding worlds beyond our solar system. Unlike JWST, which studies a handful of exoplanets in intense detail, Ariel is built for volume. Its 65-centimeter infrared telescope will operate from Lagrange Point 2, the same quiet orbital perch as JWST, but with specialized optics designed to capture the faint chemical signatures imprinted on starlight as planets transit their host stars. Imagine sunlight filtering through Earth's atmosphere during sunset. That same principle lets Ariel decode the atmospheric composition of distant worlds by analyzing which wavelengths get absorbed as their host star's light passes through their air. Water vapor, methane, carbon dioxide, each molecule leaves a unique barcode in the spectrum, and Ariel instruments are fine-tuned to read them all with unprecedented precision. The mission's real power lies in its statistical approach. By surveying such a diverse sample from molten lava, worlds to those straddling the habitable zone, Ariel will uncover patterns in how planetary atmospheres evolve based on factors like stellar radiation or orbital distance. Why do some gas giants retain thick layers of ammonia clouds while others are choked with carbon monoxide? How do rocky planets lose their hydrogen envelopes over time? These aren't just academic questions, they're clues to understanding whether Earth's delicate balance of nitrogen and oxygen is a cosmic fluke or part of a broader planetary recipe. Of course, the elephant in the room is biosignatures, combinations of gases like oxygen and methane that could hint at biological activity. Ariel won't just look for these markers, it'll assess how often they appear in different environments. If oxygen keeps popping up on planets orbiting active M-dwarf stars, for example, it might suggest false positives from stellar flares rather than photosynthesis. But if it's consistently found on worlds with water and moderate temperatures, that's when things get interesting. The mission's designers have cleverly included a Tier 1 list of 40 particularly promising targets, including TRAPPIST-1 siblings where biosignature detection would carry extraordinary weight. Beyond pure science, Ariel represents a quiet revolution in mission design. Its modular architecture allows for real-time adjustments. If another telescope spots an intriguing exoplanet halfway through the mission, Ariel can pivot to investigate. The spacecraft will also pioneer new cooling techniques, using a sun shield and a novel radiator fin system to keep its infrared sensors at a crisp -230°C without heavy cryogenic systems. These innovations could trickle down to future telescopes, making them lighter, cheaper, and more adaptable. When Ariel data starts flowing in the 2030s, it won't just fill textbooks, it'll rewrite them. For the first time, we'll have a census of alien atmospheres vast enough to spot cosmic trends, transforming exoplanet science from isolated case studies into a predictive field. And who knows, among those 1,000 spectral fingerprints, we might just find one that matches our wildest hopes, a world not just habitable but possibly inhabited. NASA's Nancy Grace Roman telescope isn't just another eye in the sky. It's a time machine, a dark matter hunter, and a planet-finding powerhouse rolled into one. Slated to launch by 2027, this Hubble successor packs a mirror the same size as its famous cousin, but with a field of view 100 times wider, allowing it to capture vast swaths of the universe in a single snapshot. While Hubble gave us stunning close-ups of celestial wonders, Roman is designed to tackle the big questions. What is dark energy doing to the cosmos? How did inflation shape the early universe, and just how many Earth-like worlds are hiding in our galactic backyard? The answers could rewrite everything we think we know about reality itself. One of Roman's most mind-bending missions involves mapping the invisible scaffolding of the universe, dark matter. Though this mysterious substance doesn't emit light, its gravitational pull warps space like a funhouse mirror, bending the light from distant galaxies in a phenomenon called weak gravitational lensing. Roman's razor-sharp optics will measure these subtle distortions across billions of galaxies, creating the most detailed 3D dark matter map ever made. Imagine tracing the outline of a shadow to deduce the shape of the object casting it. Except the shadow is the size of the observable universe, and the object is made of something we've never touched or seen. This map could finally reveal whether dark matter is cold, warm, or something even stranger, giving physicists vital clues to its true nature. But Roman's talents don't stop there. It's also the ultimate exoplanet detective, using a technique called microlensing to spot worlds other telescopes miss. When a star passes in front of a more distant star, its gravity acts like a magnifying glass, briefly brightening the background star's light. And if the foreground star has planets, they'll leave their own tiny fingerprints in that light curve. Roman's continuous gaze will monitor hundreds of millions of stars for these telltale blips, uncovering planets as small as Mars orbiting far from their star's warmth, including rogue worlds drifting alone in the void. These cosmic nomads, impossible to detect by traditional methods, might outnumber stars in our galaxy, and Roman could finally give us a census of these dark, orphaned worlds. Then there's the cosmic inflation angle. By teaming up with ground-based telescopes, Roman will study the large-scale structure of the universe with unprecedented precision, hunting for faint ripples left over from the Big Bang's explosive expansion. These patterns, frozen in time like fossilized waves on a primordial sea, could reveal whether inflation happened as theorized, or if the universe's birth was even wilder than we imagined. Some models suggest inflation created bubble universes beyond our own. Roman's data might hint at whether we're alone in the multiverse. What ties these threads together is sheer scale. Where Hubble studied individual objects in depth, Roman thrives on statistics, amassing data on billions of galaxies, stars, and planets to spot cosmic trends. It's the difference between reading a single page of history and analyzing the entire library. And with its ability to peer back to when the universe was just 2 billion years old, this telescope won't just show us where we are, it'll remind us how far we've yet to go. The universe has kept its biggest secrets hidden for billions of years. Roman was built to steal them. Russia's lunar globe mission isn't just a return to lunar exploration. It's a high-stakes gambit in the new space race, one where the prize isn't just prestige, but potentially trillions of dollars worth of water ice trapped in the moon's polar shadows. After a nearly 50-year hiatus since its last lunar landing, Russia is charging back to the surface with a series of robotic landers designed to stake their claim in the most valuable real estate beyond Earth, the permanently shadowed craters of the South Pole. These deep, frigid pits, untouched by sunlight for billions of years, are thought to hold vast deposits of water ice, a resource that could fuel everything from rocket propellant to life support for future colonies. Lunar Globe's first lander, Luna 25, is scheduled to touch down near Bogoslavsky crater in 2025, marking the opening salvo in a geopolitical showdown over who gets to tap these cosmic reservoirs. What makes this mission more than just a science project is its strategic timing. With NASA's Artemis Program aiming for sustained lunar presence and China's Chang'e missions already returning samples from the far side, Russia can't afford to sit on the sidelines. Lunar Globe's suite of instruments reads like a prospector's toolkit, neutron spectrometers to map hydrogen concentrations, drills capable of burrowing into the icy regolith, and cameras to scout landing sites for future crewed missions. But the real ace up its sleeve might be the mission's precision. Unlike earlier Soviet lunar landers that targeted equatorial zones, Luna 25 will attempt a soft landing within just a few hundred meters of its target, a feat necessary to navigate the treacherous, boulder-strewn terrain of the poles. Pull this off, and Russia positions itself as a key player in the coming lunar economy. Fail, and it risks ceding the moon to rivals. The geopolitical undertones are impossible to ignore. While NASA frames Artemis as a global collaboration, Russia has increasingly pursued its own path, partnering with China on lunar initiatives rather than joining the U.S.-led effort. Lunar Globe embodies this shift, showcasing homegrown technology like its innovative landing radar, designed to avoid the pitfalls that doomed India's Vikram lander in 2019. Yet the mission's success hinges on more than national pride. Confirming accessible water ice would validate a radical vision, one where the moon isn't just explored but industrialized, with lunar-derived propellant slashing the cost of missions to Mars and beyond. Russia's space agency, Roscosmos, has already floated concepts for orbital depots fueled by lunar water, a potential game-changer for deep space logistics. Science takes center stage too. Lunar globe samples could reveal whether the moon's water arrived via ancient comet impacts or bubbled up from volcanic outgassing, clues to the solar system's watery history. But the mission's lasting impact may be legal rather than scientific. With no international consensus on lunar resource ownership, every successful landing sets a precedent, quietly shaping the rules of extraterrestrial real estate. As Luna 25's drill bites into the regolith, it won't just be collecting ice, it'll be testing whether humanity can transition from explorers to neighbors in the cosmos without repeating the territorial conflicts of Earth. The moon's silent, shadowed craters hold more than water. They hold the future of spacefaring civilization, and Russia just placed its flag in the ground. Deep in the asteroid belt between Mars and Jupiter lurks a cosmic oddity so strange it could rewrite the story of how planets are born. 16 Psyche, a metal world unlike any we've ever visited. NASA's aptly named Psyche mission, launching in October 2023, isn't just another asteroid flyby. This spacecraft is bound for what scientists believe could be the exposed core of a failed planet. A nickel-iron relic from the solar system's violent youth that never finished forming into a proper world. Imagine Earth's own molten core, but frozen in time and floating in space. That's the tantalizing mystery Psyche aims to unravel. What makes this asteroid special isn't just its composition. Though a surface made mostly of metal is bizarre enough, but what it can teach us about the hidden hearts of rocky planets. Earth's core, buried under thousands of miles of mantle, is forever out of reach. But Psyche offers a freaky natural experiment. What if you stripped a planet bare, leaving only its metallic skeleton? The mission's suite of instruments will map the asteroid's magnetic field, analyze its surface chemistry, and even measure tiny variations in gravity to probe its internal structure. If Psyche's magnetism matches predictions for a frozen dynamo, it would confirm theories about how planetary magnetic fields form and fade over billions of years. But there's more than pure science at stake. Psyche could be the Rosetta Stone for space mining, proving whether metal-rich asteroids are viable sources of iron, nickel, and rare elements like platinum. Early radar observations suggest the asteroid contains enough metal to outweigh the global economy by orders of magnitude, though bringing that bounty home isn't the point. What matters is understanding how these resources are distributed and locked within the asteroid's structure. Psyche's high-resolution cameras and gamma-ray spectrometer will identify mineral veins and metal oxides, creating the first real blueprint for future off-world prospectors. The engineering behind this mission is just as groundbreaking. Psyche will test NASA's next-generation deep space optical communication system, using lasers to transmit data at speeds up to 100 times faster than traditional radio. Picture downloading an entire high-definition movie from deep space in under a minute. That's the kind of bandwidth that could revolutionize how we explore the outer solar system. The spacecraft will also rely on solar electric propulsion, harnessing sunlight to power ion thrusters that gently but continuously accelerate it toward its target. This efficient but slow-burn approach means a 4-year cruise before arrival in 2026, but it's a trade-off that could become standard for future deep space missions. Perhaps most mind-bending is the possibility that Psyche isn't a planetary core at all. Some models suggest it could be a rare survivor of early solar system collisions, a chunk of primordial metal left over from the chaotic era when planets were still assembling. That would make it less like a stripped core and more like a cosmic fossil, preserving chemistry from the very first moments of planetary formation. Either way, the data Psyche beams back won't just fill textbooks, it could redefine how we think about the building blocks of worlds, including our own. And if those gleaming metal planes hint at practical ways to harvest resources in space, this strange asteroid might just become the most valuable piece of real estate in the solar system. The United Arab Emirates isn't just joining the space race, it's rewriting the playbook, fresh off the triumph of its Hope probe, which captured stunning global images of Mars' atmosphere. The UAE is setting its sights even farther, a daring 11-year voyage to explore not one, but 7 asteroids in the main belt between Mars and Jupiter. Slated for launch in 2028, this mission represents more than scientific ambition. It's a declaration that the Arab world is carving out its place as a leader in deep space exploration. By 2034, if all goes according to plan, the Emirati spacecraft will have conducted close flybys of 6 asteroids before attempting an unprecedented landing on Justicia, a rare reddish space rock that might hold clues to the solar system's primordial chemistry. What makes this mission extraordinary isn't just the technical complexity, it's the breakneck pace at which the UAE's space program is evolving. A decade ago, the country had never built a planetary probe. Now it's orchestrating a multi-target deep space ballet that even established space agencies would find daunting. The mission builds on lessons from Hope, particularly its innovative, fast-track development model that delivered the Mars orbiter in half the usual time by leveraging international partnerships while nurturing local talent. This time, engineers at the Mohammed bin Rashid Space Center are pushing further, designing a spacecraft capable of autonomous navigation during years-long cruises between asteroids, where communication delays make real-time control impossible. The choice of targets reveals the mission's scientific savvy. Among the 7 asteroids, Justicia stands out as a cosmic time capsule. Its unusual red hue suggests a surface rich in organic molecules, possibly similar to compounds that seeded life on Earth. Some astronomers speculate it might even be a refugee from the outer solar system, flung inward during the planet's chaotic early dance. Landing here, a feat never before attempted on such a distant asteroid, could unveil whether these nomadic rocks ferried water and prebiotic chemistry across the young solar system. Other targets, like the metallic asteroid Egeria, offer glimpses into the building blocks of planetary cores, echoing discoveries from NASA's Psyche mission but from a fresh vantage point. But the UAE's ambitions extend beyond pure science. The mission doubles as a proving ground for technologies critical to the next phase of space exploration. Advanced ion thrusters for efficient long-haul travel, AI-driven navigation systems for deep space autonomy, and compact spectrometers capable of sniffing out water and organics from afar. These innovations could position Emirati companies as key players in the emerging space economy, from asteroid mining to interplanetary logistics. And let's not forget the cultural ripple effects. Every image beamed back will carry the legacy of Arab astronomers like Al-Battani, who charted the stars over a millennium ago. The timeline is as audacious as the itinerary. After launching aboard a Falcon 9 rocket, a nod to the UAE's pragmatic collaboration with SpaceX, the probe will slingshot past Venus in 2029, using the planet's gravity to bend its trajectory toward the asteroid belt. This maneuver, a delicate cosmic pirouette, must be executed with pinpoint precision to set up the first flyby in 2030. From there, the spacecraft will hopscotch across millions of miles, its path meticulously calculated to conserve fuel while maximizing scientific returns. Critics might dismiss this as a vanity project, but the data could reshape global asteroid science. By sampling diverse bodies in one sweeping tour, the mission offers something rare, a comparative study of how space weathering, composition, and orbit history vary across the belt. That's intel NASA or ESA would typically gather piecemeal over decades, and if the landing succeeds, Justice's surface could yield discoveries that echo the Rosetta mission's revelations about comets, but with an unmistakably Emirati stamp. More than anything, this mission signals a seismic shift in who gets to explore the cosmos. The UAE isn't content to be a passenger on humanity's spacefaring journey. It's grabbing the steering wheel, proving that with vision and determination, the stars are within reach of any nation bold enough to reach for them. As the probe's solar arrays deploy in deep space, they won't just power instruments. They'll illuminate a new chapter in the story of human exploration, written in Arabic script. While most telescopes focus their gaze on narrow slices of the cosmos, NASA SpaceX is about to perform the ultimate celestial census, mapping hundreds of millions of galaxies across the entire sky in a rainbow of infrared colors we've never seen before. Launching in 2025, this spacecraft isn't just another observer. It's a cosmic cartographer on a mission to create the most detailed 3D atlas of the universe ever attempted, revealing secrets from the birth of the first stars to the fingerprints of water on distant worlds. What sets SpaceX apart is its panoramic vision. Unlike Hubble or JWST, which study individual objects with intense focus, this fridge-sized observatory will sweep its gaze across the entire celestial sphere not once, but twice each year, capturing the infrared glow of galaxies, stars, and even asteroids in 96 distinct color bands. Imagine an artist painting the night sky with a palette 96 times richer than the human eye can perceive. That's the level of spectral detail SpaceX will achieve. This data will allow scientists to measure the distance to over 300 million galaxies by analyzing how the expansion of the universe stretches their light into infrared wavelengths, creating a cosmic yardstick to track dark energy's influence over billions of years. But the mission's ambitions stretch far beyond mapping. SpaceX's hyperspectral eyes can detect the faint afterglow of cosmic inflation, the explosive moment when the universe ballooned from smaller than an atom to macroscopic size in fractions of a second. Hidden in the pattern of galaxy distributions are faint ripples from this primordial growth spurt, and SpaceX's all-sky data will test whether inflation happened as theorists predict, or if the universe's birth was even stranger than we've imagined. Some models suggest inflation created bubble universes beyond our own. This mission might find the first hints of their existence etched into the large-scale structure of space itself. Then there's the water trail. SpaceX will scan the Milky Way's star-forming regions for the unique infrared signature of water ice clinging to dust grains, the raw material of future planets. By mapping where these icy reservoirs are most abundant, the mission could reveal how water, the essential ingredient for life as we know it, gets delivered to newborn worlds. Recent discoveries of water on asteroids and the moon suggest this process is ongoing, and SpaceX's galaxy-wide survey will show whether Earth's oceans are a cosmic fluke or part of a universal pattern. The engineering behind this endeavor is as clever as the science. To achieve its sweeping scans, SpaceX spins slowly like a top, its telescope systematically covering every patch of sky while shielded from the sun's glare by a conical baffle resembling a giant party hat. Each 6-month sweep generates enough data to fill 10,000 smartphones, all processed by algorithms trained to extract cosmic signals from the noise of interstellar dust and stray heat. And unlike JWST's decade-long development, SpaceX was designed for efficiency, repurposing flight-proven components to keep costs under $100 million, proof that universe-altering discoveries don't always require flagship budgets. When the first data releases hit astronomers' desks in 2026, they won't just get snapshots, they'll receive an entire cosmic encyclopedia. From tracking how galaxies cluster under dark matter's invisible pull to spotting organic molecules floating in distant stellar nurseries, SpaceX's legacy will be measured not in singular eureka moments, but in countless small revelations that collectively redefine our place in the universe. This isn't just a telescope, it's a mirror held up to the cosmos, revealing patterns no human eye could ever piece together alone. And in those patterns, we might finally find answers to questions we haven't even learned to ask yet. China's Chang'e 6 mission isn't just another trip to the moon. It's a daring raid on one of the solar system's most mysterious territories, aiming to bring back treasures no human or robot has ever touched. Building on the stunning success of Chang'e 5, which returned the first lunar samples in over 40 years, this follow-up venture is heading somewhere even more extraordinary: the far-side South Pole Aitken Basin, a colossal impact crater so deep it might expose material from the moon's mantle. If successful, the rocks and dust scooped up here could rewrite our understanding of how the moon formed, why its near and far sides look so different, and even whether water ice hides in its permanently shadowed recesses. What makes this mission unprecedented isn't just the destination, it's the logistical ballet required to pull it off. Unlike Chang'e 5, which landed on the familiar near side, Chang'e 6 must operate entirely out of Earth's direct line of sight, relying on the Queqiao-2 relay satellite to bounce signals across the lunar horizon. Picture a robotic archaeologist digging into terrain we've only seen from orbit, guided by remote control with a 2-second delay, all while avoiding boulders and slopes that could trap or topple the lander. The stakes couldn't be higher. The South Pole Aitken Basin, stretching over 1,500 miles wide and 8 miles deep, is the oldest and largest impact crater in the solar system, a scar from a collision so violent it might have punched through the moon's crust and flung chunks of its interior onto the surface. The samples Chang'e 6 collects could settle one of planetary science's biggest debates. Did the moon form from debris after a Mars-sized object slammed into early Earth, or was its history more complex? Minerals like olivine or pyroxene, if found, would be smoking gun evidence of mantle material, offering a glimpse into the moon's geochemical engine. But there's another prize hiding in the shadows. The basin's depths include areas untouched by sunlight for billions of years, cold traps where water ice from ancient comet impacts might still cling. Chang'e 6's drill and robotic arm are designed to scoop both surface regolith and deeper layers, potentially capturing trace volatiles that could reveal how water travels through the inner solar system. Yet the mission's true brilliance lies in its backup plans. If the primary landing site proves too hazardous, the spacecraft can autonomously adjust its trajectory, using hazard avoidance algorithms honed during Chang'e 4's historic far-side touchdown. Once samples are sealed in their ascent capsule, the lander will blast them back to lunar orbit, where they'll rendezvous with a return module for the journey home. This intricate choreography, launch, landing, liftoff, and docking, must unfold flawlessly without human intervention, a testament to China's rapid advancements in autonomous space robotics. Beyond pure science, Chang'e 6 signals China's long-game strategy for lunar dominance. By mastering far-side operations now, they're laying groundwork for future crewed missions and even a proposed international research station near the South Pole. The samples themselves will likely be shared selectively, cementing scientific partnerships while showcasing China's technical prowess. And with NASA Artemis Accords excluding China from its lunar coalition, this mission is a stark reminder. The new space race isn't just about planting flags, it's about controlling the narrative of exploration itself. When that return capsule parachutes onto Inner Mongolian grasslands in 2025, it won't just carry rocks, it'll deliver a piece of the moon's soul, forged in collisions older than multicellular life on Earth. And locked in those grains might be answers to questions we haven't even thought to ask yet. Most space missions spend years locked onto a single target, but the European Space Agency's Comet Interceptor is playing the ultimate cosmic waiting game. Instead of chasing a known comet, this pioneering spacecraft will loiter at Lagrange Point 2, a gravitationally stable parking spot a million miles behind Earth, poised to sprint toward an undiscovered visitor the moment one appears. Imagine a telescopic net cast into the solar system's depths, ready to snag the most scientifically precious game of all. A pristine comet hurtling inward from the Oort cloud for the very first time, its volatile ices and organic molecules untouched by the sun's heat. What makes these first-time comets so valuable is their frozen purity. Most comets we've studied, like Halley or Churyumov-Gerasimenko, are regulars in the inner solar system, their surfaces repeatedly baked by sunlight, their original chemistry altered. But a dynamically new comet, one making its debut plunge toward the sun, is essentially a time capsule from the solar system's birth 4.6 billion years ago. The Comet Interceptor's trio of spacecraft, released like a swarm as the target approaches, will surround the icy intruder, analyzing its composition before solar radiation can erode its surface. One probe might dive dangerously close to sample dust jets. Another could map the nucleus in 3 dimensions, while the third measures magnetic fields. Together, they'll create the most complete portrait of a virgin comet ever captured. The mission's design is as elegant as it is audacious. Unlike Rosetta's decade-long chase, the Comet Interceptor could be waiting at its post for years before the right opportunity arises. Once ground telescopes spot a promising inbound object, likely a faint speck beyond Jupiter's orbit, the spacecraft will fire its thrusters to intercept, adjusting course with precision that would make a billiards champion envious. Timing is everything. Arrival must coincide with the comet's first signs of activity, when surface ices begin vaporizing but haven't yet obscured the nucleus with dust clouds. But the real genius lies in the spacecraft's modularity. 3 independent probes mean redundancy if one fails, and the ability to study the comet from multiple angles simultaneously. The mothership carries a high-resolution camera to document surface fractures where primordial gases escape, while the smaller scouts pack mass spectrometers to sniff organic compounds like formaldehyde or hydrogen cyanide, building blocks for life that might have seeded early Earth during the late heavy bombardment. One daring subprobe might even attempt a touchdown, though landing on an object with gravity so weak requires harpoons and grappling hooks to avoid bouncing into space. Beyond pure science, the mission tests technologies crucial for future exploration. Autonomous navigation systems must keep pace with a tumbling, unpredictable target, while ultra-lightweight solar panels cope with the dim sunlight far from home. Success would prove we can react swiftly to fleeting cosmic opportunities, paving the way for missions to intercept interstellar interlopers like Oumuamua. When Comet Interceptor finally springs into action, it won't just be observing a space rock, it'll be touching the raw materials of the solar system's dawn, preserved in deep freeze since before the planets formed. And in that moment, we might just glimpse the ingredients that turned a swirling dust cloud into a living world. While most lunar missions grab attention with flashy landers or rovers, NASA, a lunar trailblazer, is proving that big discoveries often come in small packages. This suitcase-sized satellite might just hold the key to unlocking the moon's most precious resource, water. Slated to hitch a ride to lunar orbit in 2024 as a secondary payload, this nimble spacecraft carries a game-changing mission to create the most detailed maps ever of water ice hiding in permanently shadowed craters at the Moon's poles. But Trailblazer isn't just hunting for water. It's decoding exactly how those molecules are bound up in the lunar soil, whether as frost clinging to grains of dust or trapped inside glassy beads formed by ancient comet impacts. That distinction might sound academic, but for astronauts hoping to mine these deposits for drinking water and rocket fuel, it's the difference between an accessible oasis and a mirage. What sets Trailblazer apart is its dual-spectrum vision. While other orbiters have spotted hydrogen signatures hinting at water, this compact powerhouse packs two specialized instruments working in tandem. The High-Resolution Volatiles and Minerals Moon Mapper, or VM3, operates like a cosmic moisture detector, scanning infrared light reflected off the surface to identify water's unique spectral fingerprint. But here's the genius part. It can distinguish between water locked inside minerals and free ice, critical intel for future drilling operations. Meanwhile, the Lunar Thermal Mapper charts temperature variations down to individual pixels, revealing which frigid craters are cold enough to preserve ice for billions of years versus those where sunlight creeps in just enough to slowly bake it away. Together, they'll produce the equivalent of a lunar prospector's treasure map, highlighting not just where the water is, but how easy it'll be to extract. The implications for Artemis are staggering. Imagine a lunar base near the South Pole where solar panels provide power, while robotic rigs drill into nearby craters to harvest ice. Shipping container-sized electrolyzers could then split that water into hydrogen and oxygen, the key ingredients for fuel. Trailblazer's data will determine whether such visions are feasible, identifying ideal landing zones where water reserves lie close enough to sunlight for continuous operations. Some models suggest certain micro-cold traps, no larger than a parking space, might hold concentrated ice. If confirmed, astronauts could target these sweet spots rather than excavating entire craters. But Trailblazer's legacy might extend beyond practical concerns. By analyzing how water is distributed across different geological contexts from volcanic plains to impact melt deposits, the mission could settle debates about how water arrived on the Moon in the first place. Was it delivered by comets, forged by solar wind interacting with surface minerals, or spewed from ancient lunar volcanoes? Each origin story leaves distinct isotopic clues Trailblazer's instruments are exquisitely tuned to detect. The answers won't just rewrite lunar history, they'll shed light on how water, the universal solvent for life, is distributed across rocky worlds throughout the cosmos. At its core, this mission embodies a quiet revolution in space exploration, leveraging small, focused satellites to answer monumental questions. Developed for under $60 million, a fraction of traditional planetary missions, Trailblazer proves that with smart design and precise goals, even modest spacecraft can alter humanity's cosmic trajectory. When its first maps beam back to Earth, they won't just guide astronauts, they'll reveal a moon transformed from barren wasteland to a land of hidden possibilities, where every shadowed crater whispers promises of fuel, air, and perhaps even a permanent foothold beyond our home planet. Most meteor showers come from comets shedding dusty debris as they swing near the sun. But the Geminids, one of the year's most dazzling displays, break all the rules. Their parent isn't an icy wanderer from the outer solar system, but a bizarre, blue-hued asteroid named Phaethon that skirts closer to the sun than Mercury. Japan's Destiny Plus mission is about to unravel this cosmic contradiction, launching in 2024 to chase down Phaethon and dissect its mysteries. Is it a rogue comet that exhausted its ice, a rubble pile sculpted by solar heat, or something entirely new? The answers could rewrite what we know about the blurry line between asteroids and comets and reveal how life's building blocks hitchhike across the solar system. What makes Phaethon such a puzzle isn't just its role as a meteor shower generator, it's the sheer violence of its activity. Most asteroid-borne meteors come from collisions, but Phaethon spews dust clouds so intense they're visible to telescopes, especially during its scorching close passes to the Sun. Some scientists think thermal stress fractures its surface, like a baked potato splitting in an oven, while others suspect hidden reservoirs of sodium or carbon monoxide vaporizing explosively. Destiny Plus, short for Demonstration and Experiment of Space Technology for Interplanetary Voyager, will swoop within just 300 miles of the asteroid's surface, its dust analyzers sniffing for traces of these volatile compounds. If it catches Phaethon mid-outburst, we might witness first and how an apparently rocky body mimics a comet's dusty fireworks, but the mission's ambitions stretch far beyond Phaethon itself. Mounted to the spacecraft is a groundbreaking instrument called DDA, the Dust Detector and Analyzer, designed to intercept and dissect the Geminid meteoroids trailing the asteroid like breadcrumbs. Most meteor samples burn up in Earth's atmosphere before we can study them. DDA will capture these particles intact, measuring their size, speed, and composition in pristine space conditions. That data could settle a long-standing debate. Do the Geminids contain organic molecules or water-bearing minerals, suggesting Phaethon was once icier than it appears? Finding even trace amounts would bolster theories that asteroids ferried water to early Earth, not just comets. Destiny Plus also serves as a testbed for Japan's next-gen space tech. Its ion engines, powered by solar panels and microwaves, promise fuel efficiency 10 times greater than chemical rockets, a must for future missions to the outer planets. The spacecraft's autonomous navigation system, which will steer it during the high-speed flyby, could become the brains behind future asteroid landers or even Mars sample return missions. And unlike most deep space probes, Destiny Plus is compact, proving that big science doesn't always require massive spacecraft. The implications ripple beyond pure astronomy. If Phaethon's activity stems from solar heating, countless other near-Sun asteroids might hide similar volatile reserves, potentially valuable resources for future spacefarers. Its blue color, rare among asteroids, hints at exotic mineralogy worth mining, and understanding its orbital dance helps astronomers predict close passes with Earth. Phaethon's orbit brings it uncomfortably close to our planet every few decades, and knowing its exact composition could refine impact-risk models. When Destiny Plus screams past Phaethon at 20 miles per second in 2028, it won't just snap pretty pictures. It'll force us to rethink how small bodies evolve under the Sun's relentless glare, blurring the artificial divide between asteroids and comets. And tucked in its data might be clues to an even bigger puzzle: how lifeless rocks become cosmic delivery trucks carrying the very ingredients that made our world alive. While Dragonfly Plus takes the plunge into Venus's toxic clouds, its sister mission Veritas will hover above like a cosmic cartographer, using radar to strip away the planet's thick veil and reveal the fiery drama below. Where Dragonfly seeks answers in atmospheric chemistry, Veritas is all about geology, uncovering whether Venus is a dormant relic or a planet still convulsing with volcanic fury. Armed with a state-of-the-art synthetic aperture radar system, this orbiter will map the surface at resolutions down to just 15 feet per pixel, exposing features as small as a city block. That's like switching from a blurry black and white TV to ultra-high definition, finally letting us see whether lava flows are fresh enough to still steam beneath the sulfurous sky. What makes Veritas revolutionary isn't just its sharp eyes, it's how it peers into Venus's past. The spacecraft's radar will trace the subtle warping of the crust, hunting for telltale signs of tectonic activity like folded mountain ranges or rift valleys. On Earth, such features betray the motion of continental plates, but Venus lacks those, or so we think. Some scientists suspect its crust might instead shuffle in vast, slow-moving blobs, a process called stagnant lid tectonics that could explain bizarre features like tesserae, jumbled highlands resembling crumpled tinfoil. Verita's global topography map will test this theory, revealing whether these regions are indeed the scars of ancient crustal battles. But the real showstopper could be its search for active volcanism. Previous missions spotted lava flows, but their ages remain a mystery. Veritas will settle the debate by comparing its radar images with 30-year-old data from NASA Magellan probe. Fresh flows would appear starkly different, their rough surfaces reflecting radar waves in telltale patterns. Even more tantalizing, the orbiter's infrared spectrometer might catch hotspots where magma breaches the surface, something no mission has ever confirmed. Imagine discovering that Venus, not icy Europa or dusty Mars, is the solar system's other geologically active world, a place where volcanoes might still reshape the landscape under that crushing orange haze. The mission's secondary payload, a gravity science experiment, adds another layer of intrigue. By measuring how Venus's gravity tugs on the spacecraft, scientists can infer how mass is distributed beneath the surface, potentially locating hidden magma chambers or dense mantle plumes. This data, combined with the radar maps, could reveal whether Venus has Earth-like subduction zones where crust sinks into the mantle, or if its resurfacing happens in catastrophic outbursts every few 100 million years. Unlike Da Vinci's daring one-shot dive, Veritas is built for the long haul, with a planned 2-year mission to methodically peel back Venus's secrets. But together, these missions form a perfect partnership. One probes the atmosphere's ghostly whispers of lost oceans, while the other deciphers the tectonic scars of a planet that took a catastrophic wrong turn. And if they find even hints that Venus still breathes fire beneath its shroud, it would rewrite not just our understanding of this world, but of how rocky planets age and die across the cosmos. SpaceX's Dear Moon project isn't just a joyride around the moon. It's a cultural moment that blurs the line between astronaut and artist, redefining who gets to experience the cosmos. Financed by Japanese billionaire Yusaku Maezawa, this week-long Starship voyage will carry 8 civilians on a loop around the moon, marking the first fully private deep space mission in history. But what sets Dear Moon apart isn't just the destination, it's the passenger list. Instead of scientists or pilots, Maezawa handpicked a diverse crew of creatives, painters, musicians, photographers, and even a YouTube filmmaker, tasking them with translating the lunar sublime into art that could move billions back on Earth. Imagine Picasso painting Earthrise or Beethoven composing a moon sonata from orbit. That's the scale of ambition behind this mission. The logistics alone are staggering. After launching aboard a Starship rocket likely in the late 2020s, the crew will spend 5 days coasting through cislunar space, reaching a point farther from Earth than any human since Apollo. Unlike NASA's tightly scripted missions, Dear Moon promises an almost spiritual freedom. Large observation windows for uninhibited stargazing, communal spaces designed for collaboration, and even the option for crew members to live-stream their creative process in zero gravity. Maezawa's vision hinges on raw emotional impact. He wants the crew to capture not just what they see, but how it feels to float between Earth and Moon, isolated yet connected to all of humanity. Critics dismissed Dear Moon as a vanity project, but its ripple effects could transform space travel. By proving civilians can safely journey beyond low Earth orbit, SpaceX pressures regulators to streamline deep space tourism policies, a critical step toward Mars colonization. The mission also tests Starship's habitability during prolonged flights, from radiation shielding to closed-loop life support. Every meal served, every sunset watched through those panoramic windows provides data for future interplanetary crews. And let's not forget the cultural payload. The artworks inspired by this trip could become the Sistine Chapel of space age, a beacon to inspire generations. Yet the boldest experiment might be psychological. How does the overview affect the profound shift in awareness reported by astronauts who see Earth from space manifest in artists untrained for cosmic isolation? Will their creations amplify its unifying message or expose new facets we've never considered? Misawa's gamble is that their output will do more for public support of space exploration than any satellite launch or Mars rover. Whether Dear Moon launches on schedule or faces delays, its legacy is already clear. The cosmos isn't just for governments anymore. By handing the reins to poets and painters, SpaceX isn't just opening space to everyone, it's ensuring we'll have something beautiful to say when we get there. Picture a telescope so powerful it could spot a city's lights on a planet trillions of miles away. That's the promise of NAS, a Habitable Worlds Observatory, a revolutionary instrument slated for the 2040s that could finally answer whether we're alone in the cosmos. Unlike Hubble or James Webb, which glimpse exoplanets as faint dots, this observatory is being designed from the ground up for one audacious goal: to directly photograph Earth-sized worlds orbiting distant stars and dissect their atmospheres for the chemical fingerprints of life. Imagine pointing it at a star and seeing not just a pixelated speck, but a vibrant blue marble with swirling clouds and continents, a place where, just maybe, another civilization might be looking right back at us. The engineering behind this vision reads like science fiction. To block the blinding glare of parent stars, a challenge often compared to spotting a firefly next to a searchlight, the observatory will deploy a stadium-sized starshade flying tens of thousands of miles ahead of it in perfect formation. This sunflower-shaped structure casts a pinpoint shadow, allowing the telescope's ultra-sensitive optics to focus solely on the dim reflected light of orbiting planets. But the real magic happens with the coronagraph, an onboard instrument that suppresses starlight internally with precision down to 1 part in 10 billion. Combined, these technologies create a cosmic microscope capable of isolating planets so faint they're currently invisible. What sets this mission apart isn't just its imaging power, it's its surgical focus on habitability. Using spectrographs finer than any before, it'll scan for the subtle dips in starlight that occur when light passes through an exoplanet's atmosphere. Certain molecules like oxygen, methane, or even chlorophyll leave telltale grooves in the spectrum. Spotting oxygen alongside methane, for example, would be dynamite. On Earth, these gases rapidly react and disappear unless constantly replenished, often by living organisms. The telescope could also detect red edge signatures, a spike in reflectivity at specific wavelengths caused by vegetation. Finding that on a distant world wouldn't just hint at life, it might reveal entire alien forests soaking up sunlight under an alien sun. Yet the observatory's ambitions stretch beyond snapshots and spectra. By monitoring planets over years, it could track seasonal changes. Imagine spotting polar ice caps that grow and shrink, or cloud patterns shifting with monsoons. Some scientists even propose searching for artificial atmospheric pollutants like chlorofluorocarbons, which would betray the presence of industrialized civilizations. And while its primary targets will be nearby stars like Proxima Centauri and TRAPPIST-1, the telescope's designers are pushing for capabilities to peer deeper, towards systems where any hypothetical observers might now be seeing Earth as it appeared during our own planet's early epochs, dinosaurs included. The road ahead is daunting. Building optics stable enough to detect continents on a planet light years away requires materials that barely expand or contract with temperature changes. The Starshade's deployment will demand autonomous navigation more precise than any interplanetary mission attempted. And then there's the data deluge. Each observation will generate terabytes of information, requiring AI to sift for the faintest signals of interest. But if successful, the Habitable Worlds Observatory won't just be a telescope. It'll be a time machine, a census taker, and perhaps humanity's first step into a galactic neighborhood far more crowded and far more wondrous than we ever dared dream. What comes after a discovery? That's the question lurking behind every design decision. Should the telescope find even a single world with compelling biosignatures, the next logical step would be an interstellar probe, a project already in early conceptual stages. Until then, this observatory stands as our best shot at turning philosophy into fact, transforming the age-old question, are we alone, from speculation into something we might one day hold quite literally in focus. While most planet-hunting telescopes focus on small, dim stars where exoplanets are easier to spot, ESA's Pluto mission is setting its sights on a far more tantalizing prize, Earth-like worlds orbiting stars just like our Sun. Launching in 2026, this revolutionary observatory won't just count planets, it'll track their heartbeat, using ultra-sensitive cameras to detect the faint rhythmic dimming caused by rocky bodies passing in front of their host stars. But here's the twist: Pluto isn't searching blindly. It's targeting systems where conditions might mirror our own solar system's prime real estate, Goldilocks zones where liquid water could pool on solid surfaces, and where the starlight isn't too harsh or too weak, but just right for chemistry to spark life as we know it. What sets Pluto apart is its unprecedented precision. Imagine trying to spot a gnat flying in front of a spotlight from a mile away. That's the level of detection required to find Earth-sized planets across interstellar distances. To pull this off, the spacecraft carries 26 individual telescopes working in concert. Their combined gaze so stable it can measure stellar brightness changes down to 1 part in 100,000. This lets Pluto catch not just the planetary transits, but the subtle flickers caused by starquakes vibrations that reveal a star's age, composition, and even the potential habitability of its orbiting worlds. A young, active star might bathe its planets in deadly radiation, while an older, quieter one could offer a gentler environment for life to take root. The mission's real genius lies in its long-term strategy. While predecessors like NASA Kepler surveyed stars for a few years, Pluto will monitor the same patch of sky for up to 4 years, catching multiple transits of slower-moving planets in Earth-like orbits. This patience pays off in 2 critical ways. It weeds out false positives like eclipsing binary stars, and it allows scientists to calculate a planet's mass by tracking how its gravity makes the host star wobble. Combine mass with diameter from the transit depth, and you get density, the key to distinguishing between rocky Earths and gassy mini-Neptunes. But Pluto ambitions don't stop at discovery. By studying hundreds of Sun-like stars and their planetary systems, the mission could answer one of astronomy's biggest questions: is our solar system's architecture, with small, close-in rocky planets and gas giants farther out the cosmic norm, or a rare fluke? Early exoplanet hunts turned up mostly hot Jupiters orbiting perilously close to their stars, but Pluto's focus on G-type stars like our Sun might reveal more familiar planetary arrangements. If Earth analogs turn out to be common, it would suggest the universe is teeming with real estate ripe for life. If they're vanishingly rare, we might need to rethink just how special our pale blue dot really is. The observational firepower doesn't come without challenges. Operating from Lagrange Point 2, a gravitational sweet spot a million miles from Earth, Pluto must contend with cosmic rays and solar flares that could muddy its exquisitely precise measurements. To compensate, engineers built redundancy into every system. If one camera fails, others can pick up the slack. The data deluge will be staggering. Each of those 26 telescopes generates an image every 25 seconds, requiring onboard AI to prioritize which signals get beamed back to Earth. When Pluto's first catalog lands in the late 2020s, it won't just be a list of coordinates. Each entry will represent a potential twin Earth, complete with estimates for surface gravity, radiation environment, and even the likelihood of plate tectonics, factors critical for maintaining stable climates over geologic time. Future telescopes like the Habitable Worlds Observatory will use this roadmap to zoom in on the most promising candidates, searching their atmospheres for oxygen, methane, or other chemical signatures of life. More than a telescope, Pluto is a cosmic matchmaker, one that could hand humanity a short list of addresses where, just maybe, we're not the only ones gazing up at the stars and wondering who else is out there. And in that search, we might finally understand whether life is a statistical inevitability or a miracle clinging to a lonely rock in an unimaginably vast universe. Humanity's greatest dream to travel beyond our solar system hangs on technologies that still live in the realm of theory, but whose foundations are being laid today in labs and supercomputers around the world. Imagine a spacecraft that doesn't just inch toward the nearest stars over millennia, but cheats physics itself, warping space-time to cross light years in weeks. That's the promise of the Alcubierre warp drive, a concept ripped from sci-fi that's now the subject of serious NASA research. The idea hinges on Einstein's revelation that space isn't rigid, it can stretch and compress. By contracting space in front of a ship while expanding it behind, the craft could theoretically ride a wave of distorted space-time without breaking the speed of light. The catch: it requires exotic matter with negative energy, a substance that may not exist yet. Recent experiments with quantum vacuum manipulations hint that we might one day engineer such materials, turning Star Trek's warp factor into an engineering spec sheet. But warp drives aren't the only tickets to the stars. Antimatter propulsion offers a more near-term, albeit still fantastical, solution. When matter and antimatter collide, they annihilate in a burst of pure energy, offering a fuel efficiency 10,000 times greater than chemical rockets. Just 1 gram of antimatter could release the energy of a nuclear bomb, channeled into thrust. The problem: we've only ever produced trillionths of a gram, at costs exceeding $1 million per microgram. Projects like CERN, for example, are racing to improve storage using magnetic bottles, while startups like Positron Dynamics explore ways to harvest antimatter from radioactive isotopes found in space. Even a crude antimatter engine could slash a Mars trip to weeks and a star voyage to decades. For those willing to think longer term, laser-driven light sails present a surprisingly plausible path. Breakthrough Starshot's vision of microprobes propelled by gigawatt lasers could scale up. Imagine kilometer-wide sails carrying crewed ships, pushed by an orbital laser array drawing power from solar satellites. Unlike rockets, which carry their fuel, light sails accelerate continuously, reaching relativistic speeds without wasting mass on propellant. The challenge shifts from propulsion to survival: how to shield fragile human bodies from cosmic rays and micrometeoroids at such velocities. Some designs propose ships with water-filled walls to block radiation, or spinning sections for artificial gravity during century-long voyages. Then there's the wildcard: fusion propulsion. While Earth-bound fusion reactors struggle to achieve net energy gain, space offers a shortcut. In a plasma magnet sail, a magnetic field captures charged particles from the solar wind or a fusion reactor's exhaust, channeling them into thrust. The University of Washington's Dynamac prototype suggests such systems could be surprisingly compact, potentially fueling ships that refuel by skimming hydrogen from interstellar space. Other designs, like Princeton's direct fusion drive, promise to power both propulsion and onboard systems with a single reactor, enabling round-trip missions to Saturn's moons within years rather than decades. The ultimate frontier might lie in manipulating gravity itself. While general relativity treats gravity as curvature in space-time, emerging theories like quantum gravity suggest it could be a force we learn to shield or invert. Experiments with superconductors and spinning disks have reported tiny, unexplained reductions in weight, hinting at effects we don't yet understand. If controlled, gravity modulation could enable inertia-less drives, making acceleration as comfortable as standing in a room while the universe moves around you. None of these technologies are guaranteed, but their pursuit is more than engineering. It's a testament to our refusal to accept the universe's speed limits as permanent. Every equation scribbled, every lab anomaly investigated, inches us closer to a future where the stars aren't just points of light but destinations. And somewhere between antimatter storage breakthroughs and warp field calculations, we might stumble upon physics we can't yet imagine, the real key to unlocking the cosmos. Until then, each theoretical blueprint is a beacon, reminding us that the greatest voyages begin not with a leap, but with a question. From the moon's icy poles to the methane lakes of Titan, from the rust-colored plains of Mars to the uncharted oceans of Europa, these 30 missions represent more than just exploration. They're the blueprint for humanity's future as an interstellar species. Think about it, we're no longer confined to gazing at the stars, we're learning how to touch them. Artemis could turn the moon into a launch pad for Mars. SpaceX's Starship might rewrite the economics of spaceflight, making interplanetary travel as routine as air travel. Missions like JUICE and Europa Clipper could uncover the first evidence of extraterrestrial life lurking in alien oceans, while breakthrough Starshot dares to ask if we can reach another star within our lifetimes. Every probe, every rover, every telescope is a thread in a grand cosmic tapestry, weaving together science, technology, and raw human curiosity. But this isn't just about distant horizons, it's about us. Each mission forces us to confront fundamental questions. Are we alone? Can we survive beyond Earth? What does it mean to be a spacefaring civilization? The answers won't just fill textbooks, they'll reshape culture, philosophy, and maybe even our place in the universe. Imagine a child today growing up to walk on Mars because of Perseverance's samples, or a scientist cracking fusion energy thanks to lunar helium-3. These missions aren't abstract concepts, they're stepping stones to realities we can't yet fully grasp. So now it's your turn. Which of these cosmic adventures sparks your imagination? Is it the daring dive into Venus's deadly clouds, the hunt for water on the moon, or the audacious dream of a warp drive? Drop your pick in the comments, we're all part of this journey. And if you want to stay updated on which missions leap from blueprint to reality, hit subscribe. The next big discovery could be just one launch away, and you won't want to miss it. The cosmos isn't just out there, it's calling. Let's see where we go next.